Equation of path. Now, what we're thinking about is, what is the path traced out by a projectile? How can we describe it? Right? Another way to phrase that question in language you're hopefully familiar with is, what's the locus of all the points that a projectile passes through? Okay, that's what we're trying to think about. Now, what would your first guess be? Actually, let's do this on the count of three, okay? On the count of three, I want you to say, what shape do you think that matches, right? 1, 2, 3. Who said? Okay, now, a parabola is a good guess. It's a very good guess, okay? But a guess isn't enough. Sure enough, it does look like a parabola, but just looking like something is not enough of a justification. I'll prove it for you. If you take a cable or any kind of like a bridge or a string or anything like that, and you suspend it from its two ends, right? And you just let it hang by its own weight. And that looks to me like it's also kind of the bottom of a parabola, doesn't it? It looks pretty similar, yeah? And you might guess that if I kept on going, it would, they'd go up like a parabola, that kind of thing. But the thing is, it doesn't. In fact, this shape is not a parabola. It's what we call a catenary. I don't know if I'm pronouncing that right. But it has nothing to do with parabolas. I mean, it looks very superficially the same, but it's not described by a quadratic function at all. Actually, it's described by what we call the hyperbolic cosine function. If you've got your calculator there, sorry, at least on my calculator, in the middle, up the top, where you've got your three trig functions, right? You have a look at your calculator. I've got, here we go, sorry, it's sort of in the middle, right? It goes sine, cos, tan, and then there's this weird button in the middle, which you never ever used, and it says hype, right? That hype stands for hyperbolic. You press that, and then there's like trig functions come up on your screen, but they're not the trig functions you know. They're hyperbolic sine, hyperbolic cos, hyperbolic tan. They're pronounced shine, kosh, don't ask me. Okay, I didn't make it up, I'm just telling you. Okay, now what are they? They're actually, hyperbolic cosine is this function. Now you know enough to work out what that looks like, and when you graph it, it looks like this. That's what it looks like. So it's nothing like a parabola, actually, when you go down to brass tacks. So therefore, this shape, the projectile shape, looking like a parabola, is nice as a conjecture, but how do we actually prove it? Okay, so here's what I'm going to suggest. We have x and y coordinates, right? I want to work out y as a function of x. Okay, y as a function of x. The problem with that, though, is that I don't have y as a function of x. I have it as a function of t, right? And I have x as a different function of t. Okay? Now, does this ring any bells? We actually know exactly what to do with this. If you think back to end of year 11, okay? Let me try and jog your memory. Underneath this, you can make a subheading, which is eliminating parameters. What's a parameter? This parameter is this idea of a third and other variable that you can introduce into your equations, right? Which relates the two equations to each other, right? The particular kind of parametrics we thought about was, conveniently enough, parametrics of the parabola, right? So do you remember what are the parametric coordinates of a point, any point, on a given parabola? Does anyone remember? 2a, p for parameter, right? And what was the y coordinate? AP squared, good. So I want to just go back to how do you eliminate a parameter when you've got these two independent, they're sort of independent, but they're not really. These two connected equations that are connected by this numeral, okay? What do we do? Do you remember? If what I want is y as a function of x, what do I have to do? Okay, so what I'm going to do is I'll try and get p out of one of the equations, okay? And it doesn't matter which one you pick, but probably the easiest one is to go with this one. If I want p on its own, all I have to do is divide by 2a. So that gives you p equals this, okay? And you can sub that into this equation. Is this ringing bells? Do you remember doing this? Okay. So y is equal to ax on 2a squared. So I've successfully eliminated the parameter. That's what I was trying to do, right? And now, if I just multiply this out, this is ax squared on 4a squared. So a's cancel, cancel, cancel. And that's what leaves you with your familiar x squared equals 4ay, where a is focal length. Okay? So, sweet. That's how we do it. If we know what our function of x is and our function of y is, in terms of the parameter, we can eliminate it. Okay? So here's what we're going to do. We're interested in, rather than this specific parabola, we want to work out the projectiles, right? So I'm going to need to have x and y as functions of t, and then I'll go ahead and eliminate t as a parameter. Okay? So let's start off like this. Let's assume projection from the origin, okay? Which is the way we usually start off projectile questions, just because it makes the numbers easier, right? In other words, when t equals 0, x equals 0, and y equals 0. Okay, so where does every single projectile motion question begin? What do we write first? I got two equally valid starting points. It's going to be an acceleration equation, right? One or the other. Let's just start with x because that's alphabetical. Okay. So horizontal acceleration in a projectile motion question is equal to 0. So we're going to integrate up. I need to get all the way up to x as a function of time. Okay. So my first integration lands me on a constant. Okay. And this constant, where do we get that from? Do you remember? You're going to draw your rectangle, right? And it's going to have some vertical, sorry, not vertical, some angled velocity, and you're going to have your alpha there. Okay, for your initial angle. Okay, so therefore, you're going to evaluate your constant, and you're going to get v cos alpha, right? So that's fine. Integrate one more time, and you're going to get vt cos alpha plus your new constant. And because we've defined that we started at the origin, you slap in t equals 0, x equals 0, so your second constant also 0. So this is kind of our generic displacement equation for a regular projectile question. Okay? Alright, let's rinse and repeat for y. So we start with vertical acceleration being negative gravity, right? Good. So integrate once. And this constant, again, comes from this kind of rectangle scenario here, right? So instead of v cos alpha, I'm going to have v sin alpha, right? Okay, so there's my y dot. Integrate one more time. And I'm going to get minus gt squared on 2, right? Plus vt sin alpha plus my final constant, which is also going to turn out to be 0 because I started at the origin. Okay, so once more with feeling, here's my generic x equation. Here's my generic y equation. Minus gt squared on 2 plus the angular component. All right, now, remember what we did before. To eliminate our parameter, we got one of the parameters, or the parameter out of one of the equations. Okay, which do you think we should go for? Probably that one, right? Because there's only one parameter there, whereas there's two here. It's a bit of a mess. So I just want t on its own. I'm going to say, therefore, divide by, well, v cos alpha, by the looks of it, right? So I've got x over that. Okay. So now bring that over to your y equation. Instead of t squared here, and I'm going to have this minus g on 2. I'll put that out the front, just so it's a little clearer when I expand everything out. This is going to be x on v cos alpha, all squared, right? Yep. Plus v. Now, here's another t, right? So another x on v cos alpha. And there's a sin alpha. Okay. So we can tidy this up a little bit, right? Sorry, rock shit. What you've got here, think about this, okay? This is minus g on 2, and I've got v cos alpha down here. Now, g, v, alpha, all constants, okay? All constants. So this is good. what I'm getting is an x squared out here, which is sort of what we were hoping for, right? So if I put this like so, minus g on 2 v squared cos squared alpha x squared. I'm just trying to make that coefficient obvious on its own, okay? Now what do you got over here? Well, my v's cancel, right? So that's nice. And I've got sine alpha on cos alpha, so that's going to become tan. So what I end up here is with x, actually I should put the tan alpha at the front to make it a coefficient. X, okay? So you can see, maybe you want to put this in as another color, but what we've got is what we expected. It's minus ax squared plus bx negative because it's projected and it's being pulled down by gravity.